All right, so let me just share my screen real quick. Cool, can everyone see that okay?
Yeah.
Awesome, okay. So first things first, big question of the day, what's attitude? It's commonly referred to as ADCS, so you'll hear that acronym probably a lot. It just means attitude determination control system. And attitude refers to the relative orientation of one object with respect to another, and it also usually includes the angular velocity, so basically how it's rotating about each axis. What it really means, though, what relative orientation means, it's the orientation of two reference frames. So that's how you actually would measure attitude in practice. And that's kind of shown by this image here. So you have a satellite that has its reference frame, which is denoted by these unit vectors, EX, EY, and EZ. And then you have the Earth, or just any other planet, and it has its own reference frame here, and maybe another reference frame at the surface. So attitude is really all about reference frames. Now, what are reference frames? So they're just coordinate systems that you make measurements with respect to. So you can think as simply as just X, Y, Z axes, or maybe even like say, if you're looking at the Earth, there's a few very specific ones that we use for the Earth, like the Earth-centered inertial frame, which basically means if this is like the North Pole of the Earth, it kind of is like this, and as Earth rotates, these vectors are fixed in place. Or you could have one that rotates with the Earth. There's basically just a lot of different reference frames you can choose, which is probably one of the toughest parts about this, is that you need to be really consistent with your reference frames. So it's very easy to get this messed up. But one that we often use for the satellite is the body fixed frame, which I tried to show here. And it's really useful because usually those axes correspond to real physical axes. So for our satellite, we usually denote the X, Y, and Z axis, with the Z axis being the long axis. And that's what I use as well. So sometimes it's nice to have those reference frames that actually correspond to something physical, because usually they're pretty abstract. So why do we even want to control attitude? So a lot of payloads, so think basically like imaging satellites, like Google Earth, that kind of stuff, because they use stuff like cameras, they need to be really precise, which means very precise attitude control. So they need to be pointing in a very specific spot. Like say you want to take a photo of Toronto, if you're off by just a little bit, because of that really far distance, it makes a really big difference. So you need to have very precise pointing for certain things. Another reason is communication. So for those who may not know, often what you use for communications is antennas. They come in many different shapes and forms. However, some require really precise pointing in the same way that the payloads do. So that's another reason. And the third one is basically just that satellites, if they can rotate very fast, they can basically get into these spin up events where maybe like a perturbation from the environment causes it to start spinning really fast. And you can imagine that even if it's pointing the right direction, that really fast rotation could cause problems with stuff like imaging. So you definitely don't want the satellites to be rotating super fast. Now, there's different types of attitude control. There's active and passive. So active just means that it uses power. And some examples are reaction wheels, magnetorquers, control moment gyros. So that's a reaction wheel. And basically how it works is it rotates at a constant rate. But if you change the rotation rate, then kind of by Newton's third law, you'll get, that actually causes a torque. But because every action has an equal and opposite reaction, that will then cause a torque to the satellite. So by changing its rotation rate, you can provide torques about the satellite axes. One of the disadvantages is that you can get them, they call it saturation. So if they spin like really, really fast, then it takes a lot of energy to despin them, but they're very commonly used. Magnetorquers are actually very simple. They're basically just solenoids. And you can imagine if that's the coil loop, then you'll get a magnetic field that's pretty uniform through the middle. And that acts like a magnetic moment, which can basically interact with the Earth's magnetic field. And you can just change what this magnetic moment is by changing the current through the solenoid. And you can do that in a really clever way that can make you stabilize. And one of the really cool ones, I think, are control moment gyros, which basically are similar to reaction wheels. They have basically a constant rotation about one axis, but then you actually provide torque about a different axis. And the gyroscopic effect is what actually causes a torque about the satellite. Now, there's also passive control. So there's a few different types of that. So aerodynamic stabilization is kind of exactly what it sounds. You can basically set up your satellite in such a way that you can basically exploit the aerodynamic torque, and you can make it kind of stable with respect to that. This here, gravity gradient stabilization, you basically deploy this long boom with the mass on the end, and that can basically cause it to kind of be stable like this. So you would think that like the boom is at the bottom and the satellite would kind of just wobble about it like that as it orbits. And there's also a great importance to us, passive magnetic attitude control, which basically means that you're aligning a satellite axis with the local magnetic field lines, as you can see here. So it's like a bar magnet that aligns with these magnetic field lines as it orbits. So as you can see, the satellite slowly rotates as the magnetic field vector slowly changes direction as you orbit. Attitude determination is the other thing I mentioned. So it's basically estimating what your current attitude is, and you need to do it for any active control system because you need to know what your current attitude is to know what you're going to be doing. Like say, like what are you going to do with your magnetorquers? You need to know what the current attitude is. And to do that, there's lots of different sensors that you can actually use to estimate this. So these are star trackers, and they do exactly what it sounds like. They basically track the background stars, and that can give you some idea because they know where the stars would be in an inertial reference frame. So they can help you find information about what your actual attitude is based on how the stars look from the body. Magnetometers, exactly what it sounds like. You're measuring the Earth's magnetic field. And again, if you know what it should be, say in the inertial frame at your exact position, then you know what your attitude is. Sun sensors, again, pretty self-explanatory. You're kind of measuring where the sun vector is and you're comparing that to what you'd expect in an inertial reference frame. And gyroscopes are basically just used to measure the body rotation rates. So what's NEUDOSE doing with attitude? In our case, I'm sure many of you have seen like those nice payload diagrams. It looks almost like a sphere, right? And that's really important because it basically means that we can detect radiation from all directions almost equally. So unlike something like a camera, we don't actually need precise pointing for it to work correctly. Beyond that, we don't use, they're called S-band antennas, for example, which have like really tight pointing requirements. Instead, we use dipole antennas, and their radiation pattern is shown here. So you can basically think about it as oscillation about this axis causes radiation like that. But because of that, you have this null vector, which is parallel to that oscillation direction. And if that null vector is pointing towards the ground station at all, then it represents, it's called gain. So it's basically poor communication if you have this null vector facing the ground station. So our primary goal is actually to avoid this null vector pointing. So what's NEUDOSE actually doing? We're using passive magnetic attitude control. So this blue magnet here, that's a bar magnet, and that's going to be aligned with the local magnetic field lines. And that will try to ensure we don't reach that null pointing. And that's because the antennas are basically parallel to this bottom face of the satellite. So if I'll show actually on the next slide. So basically, this is McMaster, and this is like NEUDOSE's altitude. And you can kind of see that at that altitude, the magnetic field lines are actually almost pointing straight down. So you really want the satellite to have the z-axis aligned with these field lines. So one other thing I was missing, the other two axes, those are hysteresis rods. So because the torque you get from a bar magnet comes from a cross product, it actually can't provide any torque about the bar magnet axis. So these hysteresis rods are used to actually provide torque about the z-axis and to slow it down like that rotation rate. So NEUDOSE doesn't actually need attitude determination to function, but basically we're just doing it as like as an estimate to kind of see how our system's performing, like if it's performing as expected. And we're basically doing it on the ground. And since there's no actual sensors on board aside from magnetometer, we're basically estimating the sun vector using solar panel currents. We're just kind of doing it whenever we can, but it's not mission critical at all. It's just going to be something we're doing to hopefully get a good estimate of how things are working. So how do we even figure this out? We have to do simulations to actually see if our system's going to work as we expect it to. So attitude motion is kind of defined by these differential equations. I won't go super into them, but some of the key points here is these omegas represent angular velocities about the satellite axes. These t's represent torques. So these are kind of differential equations of motion for rotation. So they're all coupled, as you can see. So that kind of makes things more complicated. You have to integrate them together. But the key takeaway I want to talk about is this T, these torques, that's external torques acting on the satellite. And there's a lot of those that actually happen in orbit. So some of the ones accounted for our gravity gradient, which basically it's similar to what you would think about when you hear gradient. It's kind of like just think, for example, like the satellite is like this, and the top of the satellite is further than the bottom of the satellite, the Earth, and that means that there's actually like a difference in gravitational force, and depending on attitude, that force difference can actually translate to a torque. Aerodynamic torque, it kind of comes from aerodynamic drag force, but because this is a rigid body that has different faces, it's very likely that there's kind of going to be different forces acting on different faces, which will overall cause a torque. Solar radiation pressure comes from photons coming from the sun, and photons can impact momentum onto the surfaces they hit. And similar to the aerodynamic torque, depending on how it's oriented, that can cause a net torque. Eddy currents basically means that our structure is metallic, and if you have this kind of rotating metallic structure in the magnetic field, it can induce these eddy currents, which are basically like current loops, and they in turn generate magnetic moments, and that's like a destabilizing torque. And lastly, the magnetic residual torque is kind of just like residual magnetization left in the structure and satellite components, stuff like that. So I just want to briefly show some of the results that we've got for this. So this basically shows our system decreasing its angular velocity days after deployment. So you can see that the X and the Y rate angular velocities, they decrease pretty fast, but the Z axis takes a lot longer. And that's just because it's the hysteresis rod that's slowing it down around the Z axis, whereas the X and Y axes are getting torqued by the bar magnet around the Z axis. And this pointing arrow here, that represents basically the error angle between the bar magnet, so the Z axis, and the local magnetic field lines. So these are just basically some of the torques I was talking about. So this shows kind of the relative order of magnitude of the torques. As you can see, the bar magnet torque, as you'd expect, is kind of dominating things. This just kind of shows like how they scale on a log plot. And this would be about the Z axis. And this is the last kind of interesting thing I want to talk about. The whole point of this was improving communication. And so this is basically an illustration showing that during communication windows, we're actually improving things with this system. So in the green, that's basically if we didn't do any attitude control. And as you can see, this pointing error angle, that's actually pointing error for communication. So the higher that error angle is, and I guess it'll, once it gets over 90, then it'll start decreasing. But essentially like a high error angle for that means pretty bad communication. It means you're getting closer to that null vector pointing. So as you can see, so this is basically like an east, a west pass, and a pass that's almost directly overhead. So directly overhead, you can see we actually get really good communication. The pointing error angle drops to pretty much zero directly overhead. And it's a lot lower than the other cases for the east and the west passes. Yeah, so that's all I had for today. Thanks everyone for listening. Does anyone have any questions?
I guess I have a question, or
Yeah,
potentially two, but maybe first to just ask how you came up with those communication simulations.
Yeah, for sure. So it was partly Dia who was working on it. So what she did basically was she modeled the ground station antennas and the satellite antennas, and using STK, you're basically able to figure out based on how those antennas, they have like what's known as a minimum elevation for the ground station. So it's basically like how high the satellite needs to be in the sky for the ground station to be able to communicate with it. So based on that, you can basically communicate access, which is when the satellite can actually communicate with the ground station. And so she basically looked at different passes, like say like a pass that was like really far east of the ground station, or one that was really far west of the ground station. And then we analyzed the pointing error during those passes, because we wanted to kind of see how it would look in typical passes, as opposed to like one that's like directly overhead, which is a bit less, which happens a bit less often.
I think my other question would be if you could walk us through like the process start to finish in developing our attitude control system. And that would probably be like from the very initial things you might have done, anything like potentially like determining reference frames or like figuring out how the system works, to where we are now, where everything is like pretty much figured out.
Yeah, for sure. Yeah, good question. That definitely takes things back. Yeah, I guess I would start back in 2019 when I didn't know like anything about attitude, and I was kind of just reading the literature on like on the systems, but just attitude in general. So one of the first things I had to figure out was how I was actually going to do the simulations. Because one of the things I actually decided on doing was decoupling the orbit and attitude propagation, just kind of because of one, it would be better because I was just using my computer, so it would take a lot less computing power to do that. And two, my original plans was basically to have MATLAB kind of do the attitude work and STK while it was doing that, do the orbit propagation, and those kind of be working simultaneously. But it turned out STK actually wasn't capable of doing that. It was only able of, it's only capable to basically just run its own simulations and get data. So that's what I ended up doing. I basically decided that I would decouple it because all I need from the orbit propagation was pretty much just like some of the physical parameters. So like what's the magnetic field vector at time step? What's the air density at time step? What's what's the position vector from the satellite to the center of the Earth? And that would help me calculate those external torques, like the bar magnet torque and all that kind of stuff. So once I figured that out, then it kind of it got to basically constructing the like the MATLAB simulation. But in terms of the reference frames, that was not the easiest. I would say it kind of came down to what reference frames STK actually provided the data parameters in. So I ended up choosing the Earth-centered inertial frame. And that was partly because STK offered all the data parameters I wanted in that reference frame. But it actually didn't matter too much whether I chose that one or a different one, as long as I was consistent. That was the big thing. You just have to make sure you're using the same reference frame for all things. Otherwise, it can get just a little confusing. It doesn't quite work out. So once that happened, it kind of just became it just took a while to build up the simulation with all these effects in MATLAB, basically. So one thing I did use, I'll share my screen again real quick, actually. One sec. So in here, where do I have those differential equations? Yeah, so the Q's here represent quaternions, which are basically like a representation of attitude. So there's a lot of different ways you can represent it. Quaternions are just one of the most efficient ways. But the thing with them is their unit length. So you need to make sure they stay normalized, and MATLAB's like ordinary differential equation solvers often wouldn't preserve that. So I actually had to modify like I think ODE 4.5, and then the one I actually used was ODE 1.1.3. And basically I had to modify those differential equation solvers like at each integration step in MATLAB's code to renormalize the quaternions at each integration step. Otherwise they decay, and that then the results didn't really mean anything. So that was probably something that took a while to figure out, because for a little while I wasn't really understanding what was going wrong, and it took a while to figure that one out. But after then, I think the most challenging thing was just making sure I was modeling these torques correctly. So one of the challenging ones is the air density. It's actually more complicated than you'd think because the air density varies seasonally and year to year, because it's kind of a function of solar flux and the magnetic index, which change through time a lot as the sun goes through its like sun cycles. So yeah, I guess once that happened, one of the other things that happened actually was initially we thought that we were going to use the y-axis, so one of the short axes for stabilization. And I'll say why that was in a second, actually, because what we thought it was actually like a wrong assumption, is that because the Earth's magnetic field looks similar to a dipole field, it actually is almost parallel to the ground, but that's actually only true if you're far from the Earth. When you're close to the Earth, like we are, it actually almost goes nadir. So our original design using the y-axis was not going to give us good communication. And that's kind of shown here. So see how like this is the z-axis case in blue. So the y-axis case is seen in red, and it's really a lot less stable, and it's not necessary, and it's not really as good. So that was kind of one of our big takeaways, that we had to change that alignment axis, and that was not too long ago. That was just like the end of last semester as we figured this stuff out. Yeah, I think that answers the question. Hopefully that answered it. Any other questions about that?
I was going to ask about aerodynamic drag.
Yeah.
usually the term aerodynamic isn't something that we associate with things in orbit. So
Mhm.
I was wondering exactly how significant that is. I know you just mentioned that, just what you mentioned now about how it's seasonal.
Yep.
So how different is it at its peak versus at its lowest point?
Actually very different. Like it can vary by an order or two of magnitude of the air density. Because like the aerodynamic drag torque is like directly proportional to the aerodynamic drag force, which is like the 1/2 like rho a c d v squared. So it's directly proportional to the air density, which can vary like I think about at one or two orders of magnitude. But these are kind of like the overall external torques. One of the key things here actually is the torques about the z-axis is this right plot, and that like orangish one there is actually one of the most significant torques about the z-axis. That's the drag torque. So it's not insignificant at all. The reason why it's significant, more significant than you might think, is because the satellite's orbiting at around around 8 kilometers per second. So even though the air density is really small, like on the order of 10 to the minus 12, it's proportional to the velocity squared, and we're
Right.
orbiting at like almost 8,000 meters per second. So it's actually pretty significant for like for a satellite there.
Yeah, awesome.
And
Thank you.
yeah, no worries. The other thing I guess I would say, it's especially important because we're not using an active control system. So like if we're using an active control system, it would be less of a problem because you can apply way more torque, and it's just in general, like it's easier to control. But yeah, considering we're using the passive system, it makes a much bigger difference.
I guess a follow-up to that, I know this is something that's kind of um, a little more out there, but would it be worth changing shapes of satellites in order to mitigate that aerodynamic drag? As you see like planes having more aerodynamic shapes, or is it not
I
worth
personally
that?
don't think so. No.
No?
I think one, most satellites use active control, so it's
Right.
like they don't really worry about it as much. The only reason they think about aerodynamic drag at all is just in terms of mission lifetime, because like the drag force is why like LEO satellites only last for up to like I don't know a few years.
Right.
So that's like a completely different thing. But the ones that use passive control, like often like they have less like stringent attitude requirements anyways. So it's like I think it's just a small enough effect that like very few people care enough about it, and the
Right,
ones who do.
to do that.
Yeah.
Interesting. Awesome.
Yeah, I
Thanks.
feel like yeah, no worries. I feel like there's a lot of advantages of the current CubeSat like kind of shape, like like whether it's like going out with like a NanoRacks deployer or stuff like that. I just feel like the whole rectangular prism probably has advantages of its own
For
that
sure.
outweigh this small effect. Cool. Yeah, great questions, everyone. Thanks for all that. Any other questions? Anything I say unclear? Because I know I have a tendency to kind of talk fast sometimes, especially from earlier on, like reference frames and like just kind of overall attitude stuff.
I actually found your pacing to be excellent throughout this presentation.
Oh, cool.
I
Okay.
agree.
Cool. Okay, I was worried I was going a bit fast. Awesome. Does anyone have any other like questions, comments, stuff you want to chat about the presentation? Oh, okay. Cool. Well, thanks everyone for coming out. I hope you all learned something. Yeah, what did everyone think? Like, did you feel like it was informative? Any feedback?
Yeah, I personally thought it was really well done.
Yeah,
Cool.
I agree, especially for something that's very theoretical. I think it really helped to bring it to light and explain it, because I think a lot of people might have trouble with it.
Mhm.
So thanks. I thought
Awesome.
it
Well,
was
yeah,
really good.
well, I'll definitely post the recording once it's like finished saving, and hopefully other people will have a chance to give it a watch. Cool. Well, if there's no other questions, then I think I'll stop recording.